All right, so today we are going to have a short little mini lecture about chapter 12. This is talking very, very, very briefly about intramolecular forces, which is a topic that you can really spend hours and hours and hours and hours discussing, and we're just going to barely scratch the surface on in this class. And then we're going to talk about water and its uniqueness and how we conserve it in nature and where we find it and all the impacts of water on society. So that's going to be the bulk of our discussion today, but we are going to discuss intermolecular forces as well. So I abbreviate intermolecular forces as IMFs. Inter means in between, like, you get on interstate, goes in between states. Molecular means with molecules. So intermolecular literally means in between molecules. And these are forces of attraction that occur in between molecules. And so if we didn't have intermolecular forces, everything would be a gas, because these, if you could imagine the molecules as little tiny balls, right? Here are the gases, here are the liquids, here are the solids. The gases on the end are on the left are not attracted to each other at all, 0% attracted. In the solid phase, they're extremely attracted to each other. They're attracted to each other so much that they stay locked in place, and that's what gives us our crystalline solid. And then here in the middle is kind of the middle of the road between these two extremes, and the molecules are attracted to each other quite significantly. And how significant that attraction is determined by intermolecular forces. And again, we are just scratching the surface in this class in World of Chem. We are not going to go deep, deep, deep into this subject. If you would like to explore it further, take some more classes in chemistry and you will spend a lot of time on this. But right now we're just talking about it from a very basic level. So when something evaporates, that means it goes from the liquid phase to the gas phase. And so if a molecule has strong intermolecular forces, that means that it's got a very high boiling point, because that means you've got to put a lot of energy into these molecules in the liquid phase to get them up into the gas phase. And then in the solid phase, again, these molecules are so attracted to each other that they are in a crystal. They're not going anywhere. So there are three types of intermolecular forces that we're going to discuss in World of Chem. There's dispersion forces, or some textbooks call them London forces, or some books just call them London dispersion forces. You'll call it all three. There's dipole forces, and then there's hydrogen bonding. And that name's kind of ambiguous because it's not actually a chemical bond. We'll talk about that in a second. So London forces can be very strong if a molecule is very big. When you take organic chemistry, for instance, you're going to talk about London forces of big molecules versus small molecules. And when you take biochemistry, you'll talk about big molecules versus small molecules. Here in World of Chem, all we're going to do is focus on our small molecules. Okay, so because we're only focusing on small molecules, we're going to say London forces are very weak, and they result from the random motion of electrons. Now, I have a video on YouTube on my channel that really gets into how this works, and I would rather you just go watch that video because it's a 3-minute discussion that gets it pretty straight to the point. Dipole forces occur in polar molecules. So polar means it's got a positive end and a negative end, just like a battery. And so molecules that have a positive end and a negative end act like little magnets, right? The positive part of one molecule is attracted to the negative part of another molecule. And if you're non-polar, that means that there's no positive end or negative end. So water is extremely polar. Vegetable oil is non-polar. And this is why they will always separate into layers. Excuse me, because they are incompatible with each other. No positive and negative ends. This one does have positive and negative ends. So no matter how much you shake it or heat it or whatever, it's not going to dissolve in each other. And then hydrogen bonding occurs when a molecule contains a nitrogen hydrogen bond, oxygen hydrogen bond, or a fluorine hydrogen bond. It's a very strong attraction, and this is the strongest intermolecular force that we will learn. And again, we're really just scratching the surface here. But what I would like you to do, please, 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 is go watch these videos on my channel. Here are the links, so you can either watch them from the playlist directly on the YouTube channel, or you can look for them on the course website. They're both there, or even if you download these notes should, the links should work in the notes as well. But these are both like very short 3 or 4 minute videos that explain and give examples of each one of these. And I really would rather you do that than me spend time in this mini lecture talking about it. So please, 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 please go watch them. What about intermolecular forces do I need to know as a World of Chem student? Number one, they are forces of attraction that occur in between molecules. Number two, for this class, we're going to say London forces are the weakest and hydrogen bonding is the strongest. And most importantly, this is why it's in bold, water is a very unique molecule with very unique physical properties because of its intermolecular forces. And that's kind of the take-home message and why we spent all this time talking about IMFs, so that we can lead into water and how great water is, which I'm not being sarcastic. Water really is great. Water is the most common liquid on Earth, and it's a highly, highly unusual molecule. It's not something that most people stop and think about unless you're a chemist, but water is a really strange molecule and it has some very interesting properties. It's very polar. Remember when we talked about 5 minutes ago, when we talked about hydrogen bonding, it occurs when molecules have an OH bond. Well, water has 2 OH bonds. And so water actually has a negative end right here on top of the O and positives down here on top of the hydrogens. If you could imagine it like in 3-dimensional space, that's what it would look like. Here's the oxygen atom, there are the 2 hydrogens. So this oxygen atom is negatively charged and these 2 hydrogens are positively charged. So it's like a little magnet. It's a small molecule in terms of its size. It's very small, but it's got a very high boiling point. You wouldn't expect a molecule that small to have such a high boiling point, but it really does. It boils at a really high boiling point compared to other molecules of the same size. And one of the neat things that you probably haven't stopped to think about is that water expands when it freezes. So if you think about, I don't know, you can go outside and observe this anytime in the winter, but if you leave ice sitting out in a bucket, for instance, and then you leave water sitting out in a bucket, you come back the next day and you check it, the bucket might actually be cracked because it expands. Water expands when you freeze it. And that comes from the structure of ice. But what you really want to think about is this has a big impact on nature. Okay. If you're talking about other substances, most substances, when they become solid, they actually sink. So if you're talking about any other substance, really, when it becomes a solid, when it freezes, it would become more dense. Water, on the other hand, becomes less dense when it freezes. And so how is that important to us in the world of chemistry? Well, because water in the ice phase is less dense than liquid water, it'll actually float. So if you've got a lake and it's wintertime and the ice floats on top, that preserves life for all the little frogs and fish and everything in the water. And if that didn't happen, if all the ice just froze and then sank and then froze and then sank and froze and sank and froze and sank, the whole pond would freeze solid and it would kill all the critters in there. So it's actually really, really important for marine life that less dense ice floats on top of liquid water. Also, when you think about erosion, right? So you think about water falling into the little tiny cracks and crevices on mountains, on your sidewalk, wherever. Water gets into those little crevices and then it freezes and then it expands. And so those cracks become bigger and bigger and bigger and bigger and bigger. Over time, that erosion process occurs because water freezes and it expands when it freezes. You may have heard this in your biology classes. I know a lot of students have told me that they've heard this in biology before, that water is the universal solvent. What that means is that a lot of substances dissolve in water. A lot of organic and inorganic compounds dissolve in water. And that's really important to society. It's really important to living things. It's really important to us. Water is a big component of our blood. And so when you talk about water and where it is on Earth, only a very small percentage of it is in ready to go form, like lakes, streams, et cetera. Look, it says your book says it's about 0.014%. That's not very much. Oceans are the primary form of our water. The 2.6 is in ice caps, glaciers, and groundwater. And so our land water that we have here on land, AKA lakes and streams and rivers and all that good stuff, that's called land water. And we get it from the hydrologic cycle, which you probably better know as the water cycle. I used to teach middle school. We did this every year. And so you've probably seen this at some point in your life. Water from the ocean evaporates. What does that called? It goes from the liquid phase to the gas phase. That's evaporation. All right. And then condensation up here in the clouds over here. Condensation, so it's gas, it condenses into the liquid phase. So going from gas to liquid, that's called condensation. And then it falls down to the earth as precipitation. And then this runoff, right? This is the water that runs down the mountain, runs down the creek, back into the ocean, or maybe it goes into the ground and collects in the groundwater. That process is actually really slow, by the way. A lot of people visualize groundwater as these like underground rivers, and that's not usually what it looks like. It's a very slow process. But nonetheless, this process we call the water cycle. Again, you're probably pretty familiar with it. Let's talk about pure versus polluted. Virtually none of the water that we have is pure. You really can only make it in an experiment in a lab. Like if you want to make pure H2O and nothing else, go do an experiment, because otherwise you're not going to have just plain H2O with nothing else. The water we're familiar with is a mixture. It contains lots of elements and compounds, a lot of stuff in there. And some of those components in drinking water are harmful and some of them are not. So if you've ever been told that you have hard water, that means that your water is rich in calcium and magnesium. Now, this isn't going to cause any health effects for you, but it's not pretty, right? When you've got your fine china or you've got your, fancy silverware sitting out and it's got scaly deposits on it, you might not like that so much. It also can make your dishwasher not be so effective. It can make your bathtub get a ring on it. All of those are not pretty to look at, but it's not going to hurt you. So you can remove all that through a water softener system. You can have one installed in your house. Maybe many of you do. If you do, it's probably set up something like this. There are some other contaminants that can get into water, and these are the kind that you really don't want anything to be part of your water. These are microorganisms. They cause disease. Their primary source is waste, right? So human waste, animal waste, and it's entering your drinking water. And this is the bad stuff. Like you really, really, really don't want this in your water. There are also chemical contaminants like industrial waste entering the atmosphere. We actually, in our previous lectures, talked about emissions coming from factories, right? So they're emitting these chemicals into the gas phase, and then they're coming into the clouds and making acid rain. So chemical contaminants can get in from industrial waste in the atmosphere. Pesticides and fertilizers can end up in your drinking water just from runoff and all that kind of stuff. And then if you just go dump your paint and your oil down the drain or straight into the ground, that can cause chemical contamination as well. When we talk about organic contaminants, we're talking about major classes of volatile versus non-volatile. Volatile just means how easily does it evaporate. And they can come from a variety of sources: fertilizers, gasolines, pesticides, paints, solvents, right? So when you think about gasoline, for instance, when you're pumping gas, you can really smell it, right? Because it's volatile. It means it goes easily into the gas phase. So these organic contaminants, you get them into our water, they can have a lot of problems: increased cancer risk, liver damage, and endocrine disruptors, and all sorts of stuff. And if you live in an area that is near a radioactive source, then obviously radioactive contamination could be something. It's usually coming from natural sources, like it's just a part of how the earth is made in your particular area. But of course, if you live next to a place where there's been a nuclear meltdown recently, you would also have that as well. So in 1974, the Safe Drinking Water Act was passed, and it set something called maximum contaminant levels, MCL. So basically what that means is that if you are a city and you provide public water, you need to sample and test your water every year. And it has to be within those levels of contaminants. I know here in my town, every year, I think it's in the spring, they send out a report to all of the people who drink water from our municipal water supply. And it literally breaks down every single contaminant and what the value was and what the threshold is. And ours has always passed. Woohoo! But you can actually go request that for your particular city. It is public available information. So they are required to notify if there are any violations, both the government agencies and you. And then the Environmental Protection Agency requires suppliers to add substances to the water to prevent contamination along the way. But just FYI, once the water is at your house, if your pipes are icky and gross, that can create other contamination that obviously the city can't control. So you do have to be careful about what's in your pipes. You know, if you've got lead pipes, obviously that's not good. So be aware of that as well. So here are some of the contaminants that, for instance, you would see on one of these reports. Our report is really long. The one that our town sends out is about 3 pages long. But it gives some biological contaminants. And what's the accepted level? 0. You don't want any of this in your drinking water. 0. So that's not acceptable. Here's some examples of some volatile organics and what would be acceptable, and some non-volatile organics and some inorganics and some radioactives, right? So this is just kind of a quick picture, but if you look at one of the real ones, it would be significantly longer, and they're neat to look at. I mean, I'm a chemist, so I like looking at that kind of stuff. But even if you're not, you can request that or just wait to get yours in the mail. If you've ever wondered about public water treatment, you have to go through a very complicated process, which is good. You want your water to be treated and safe. So you get it from your source, whatever that source is. It goes through a wire mesh screen. That's to get out all the trash and dead fish and whatever else is in there. Coagulation means, so chemicals are added to the water to cause the algae and the dirt and all that stuff that still fits through the screen to coagulate. Coagulate means to clump up. And then they go into these big tanks where literally all that solid stuff just settles out. And then it goes through some sort of either filtration to get that settled stuff out. And then you can either go the activated carbon way or the aeration way. And then depending on which city you're looking at. And then the last step is the chlorination stage. And that's to kill bacteria and that sort of thing. Once the water gets to your house, you can do things to make it taste better, smell better, look better. So for instance, if you have a water softener to treat your water to remove that hardness, that's something that you can add on once you get to your house. The EPA says if it comes from a public provider, it should be treated adequately. But then other people say, well, you know, maybe it is, but I still want to look. I don't want that hard water, or I don't want that, you know, ring or whatever. So one of the ways that you're probably familiar with is by buying one of these water pitchers with carbon filters in it. They're not that expensive. I mean, it's a lot less expensive than some other options out there. It removes a lot of those flavors that many people don't like. And then this is something interesting about getting salt out of water. So that's what desalination means. And so osmosis is something you're probably familiar from your biology class. Osmosis is the spontaneous motion from an area of higher concentration to the area of lower concentration. So for instance, if you've got a drop of food dye, right, that's very concentrated, and you've got a bucket of water that has no food dye in it, you drop that drop of food dye in, that's a drop with high concentration, and it'll spontaneously move throughout the bucket so that the whole bucket is eventually whatever color you dropped it in, right? That's osmosis. So reverse osmosis would literally be taking all that food dye and getting it back into a drop. That's a non-spontaneous process. That's something that you have to put forth work to have happen. And so what happens is you've got a semi-permeable. You may have heard that word from your biology classes. That means it can go through this mesh. It allows water to pass through, but blocks out other substances. The water containing, the side containing salt water will rise as fresh water flows into it. So you apply some pressure to it. All right, so in summary for this, we've got a discussion on melting point, boiling point, volatility. So melting point and boiling point and volatility are all from the result of intermolecular forces, dispersion, dipole, hydrogen bonding. And please, 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 please go watch the short little videos on those. We've talked about the properties of water. The physical properties of water primarily come from its structure, how it's put together, and these intermolecular forces. And as a society, we learned that water is one of the most precious resources. Societies live and die by water, and we need to do everything we can to keep it clean, safe, and drinkable. So I hope this was helpful for you, and I will end this meeting and hope you have a good day. Bye.